Hello everyone, my name is Yue Zhang and I'm a PhD student from Vanderbilt University. And today I will talk about our work CodeACT-R, a cognitive simulation framework that models how programmers virtually read and understand code without the need of any large eye-tracking data set. Reading code is not just passing the syntax. Developers focus on key points like data flow, control flow, variable definition, and return statements. Prior study had used the eye-tracking data in many ways, like the attention data has helped us study comprehension difficulty, and also it helps to train models for code summarization and error detection. Like the previous work, iTrans has leveraged the human attention data to improve performance of transformer model. Researchers even conduct code reading with brain activity, like work as aligned fMRI signals with code understanding. This shows human attention in code reading is a strong bridge between humans and tools, but getting enough case data is hard. First, eye-tracking data are slow and need lab environment. Also, large efforts still collect data from only dozens of people. Data augmentation like that from the computer vision only creates the unrealistic, uniform attention patterns that don't reflect the human cognitive, and this causes a data bottleneck for attention-guided AI model training. For example, imagine training a model on how human reads code, but you only have 40% space. That's like you try to train an LLM with one chapter of text. So we take a different path. In our approach, we try to simulate human attention during code reading based on cognitive simulation. We base it on a cognitive framework called ACT-R, and this gives us human-like attention at scale. And the pipeline is like that. First, we collect a small set of human scan paths, and in our approach, we collect the human scan paths for 48% based on code comprehension task. And we use that to build our CodeACT-R model, and then we generate many human-like scan passes for the new code. What is ACT-R in its plain terms? ACT-R is the adaptive control of thought rationale. It models how we see, remember, and decide. It is a long-standing framework in cognitive psychology, and it has modeled tasks like manual suggestion and driving. And here are core parts we use. Firstly, the buffer. Buffer holds the current goal, what you see or what you just recall. And also the decorative memory stores the facts and past experiences. And procedure memory holds the if-then rules, which is the production rules. And motor executes action like moving the eyes. So let's see how a step runs. First, the visual model encodes what you see. The information stores in the visual buffer. Then the model records what it needs. The production rule tests the buffer contents, and if some rules may fit, the system picks one rule to fire. The rule requests an action like retrieve effect, move eyes, or press a key. And the buffer changes the cycle repeat. The loop runs many times per second and drives the behavior. So how can we adapt this to the code comprehension? We encode a snippet so that visual goal buffer can see the structure, and the rule proposes the next fixation, which is the lines humans are more likely to look at, and the retrieval can favor lines the past humans look at in their similar code when it is available. We store the code semantic and human scan passes in the decorative memory. For each statement, we store the semantic category like the calculation or declaration and control level. also the complexity. We use the production rules to guide the next place to look at. We use three strategies in our approach: the semantic matching, quick matching, and cache matching. What exactly goes into memory? Then we generate a schema step by step. And like in this demo shows how the CodeACT-R work. Like the left screen is the input code, and the CodeACT-R can simulate a statement level scan path with different seed. To evaluate our approach, we consider two scenarios. First is the zero reliance, which means no prior human attention available on the code snippet, and also few reliance, and we seed it with several real-world passes for the code snippet. And there are also two metrics: AVSL, the average value sensitive Western distance. It measures the similarity to human attention using a distance that parallels longer jump. And also the coverage, which measures the percent of unique real-world patterns we can capture. Also, we have two baselines, the DMS or the VCS. DMS is the decorative memory scan path. It's a random scan path whose length is sampled from the entire dataset. And the VCS is a random scan path which the length is sampled from the real-world scan path of the target snippet. We generate 300 samples per snippet for robust comparison. And here's the result. And the top plot is the AVSL. The y-axis shows the AVSL distance. Recall is the lower the better. The x-axis is the total number of simulation runs. And the points are grouped by the model type and the field reliance level. Like the field reliance level is a percentage of 9 test scan paths used as human seeds. And 0% is just a zero reliance case. We can see from the top slot, the AVSL is lower than the baselines, so which means our CodeACT-R can simulate scan paths close to the real-world ones. Also, for the bottom figure, the y-axis shows the percent of unique human patterns covered. Like we can see the coverage rises with more reliance, and at peak, it can cover up to 87% of real-world human attention patterns. So what is the implication of our study? For research, this is a cheaper way to get cognitive signal at a scale. And for the AI training, we can train models on human-like attention for tasks like summarization, bug finding, and review. So next, we will release a large simulated attention dataset and fine-tune RM on that. And that's all for the presentation.